run through very quickly some of the kind of domain knowledge that we need to actually understand what GeoTessera does and why it's useful. So the opportunity. So we got many pressing problems. I'm sure I don't need to motivate it to this audience, but we have problems in food security, climate change, biodiversity loss, and these are all problems where having timely, accurate answers to how the surface of our planet is changing can be key to coming up with solutions to these problems. So we have these pressing problems. At the same time, we have significant amounts of remote sensing data that's freely available. Right? There's gigantic volumes of data. So we've got things like Sentinel-2 and Landsat. These are multispectral satellites, so they're a bit like you have your RGB channel in photos your camera takes. These are like that, but with some additional channels that are very useful for certain kinds of tasks you might like to do. Then we have things like MMAP. These are hyperspectral cameras. So they, instead of having 3 or 9 different spectral channels, they may have hundreds or thousands of different spectral channels. But obviously, for the spectral resolution, you trade off temporal resolution and spatial resolution for that. Then we have things like Sentinel-1, which is synthetic aperture radar. We have JEDI, ISAT-2. These are laser satellites. All this data is available. But using it is hard, right? The first thing is there's a lot of it. So a single analysis over 8 years, just using one set of multispectral, one multispectral constellation would be about 250 gigs of data for a single point on Earth. So it soon becomes prohibitive to do analyses over long periods of time at large scales. And that's if you know what data product you want. So for example, Sentinel-2, there is 2 or 3 different levels of product you could have that have various different properties, and each one has different processing baselines. So you've got to decide all that up front, and it requires significant domain knowledge to actually get started in this. But the second problem, actually, is that the optical satellites have, which is the bane of all remote sensing specialists' existence, is clouds. Like, we cannot see through clouds. They obscure what's underneath. And so for analysis, and actually a lot of computation, what we do is we build composites. So what we will do is we will take a stack of images of the same location, and we will take all the pixels that are not clouded, and then we will kind of smoosh them together. So we'll do something like take the median or average them. And you get these beautiful kind of cloud-free images, but you've thrown away all your temporal information. And that temporal information is crucial for things like vegetation, where phenology, how the spectral characteristics of a plant change over time, are very useful for identifying what type of vegetation that is, right? So can we dramatically improve the productivity of working with remote sensing data? And that was part of the motivation for the project that we started at the university called Tessera. Now, I'm not going to dive into too much depth on the actual model itself. There's an archive paper that gives you all the gory details. But at the high level, Tessera is an encoder model. So the way to intuitively think about it is if we have 2 different sets of observations of the same point on Earth, the representation, or as we call it, the embedding of that point should be the same. So if you have 2 different views of something, it should result in the same representation, so the same kind of semantic. And we built this model, and then we trained it on 800 billion non-cloudy pixel-wise time series. So we trained it on individual points on Earth, so 10-meter resolution. And what we get is we get 128-dimension embedding. So we get embedding or representation for every 10 meters on Earth. And what you can then do is you can then train models on top of that embedding. You can treat that embedding as a compressed representation of the last year's worth of observations of that point on Earth. And because we've actually done the work and spent the compute in learning those semantic features, you don't need to spend precious labels, supervised labels, like this is a tree, this is a field. You don't need to spend that when you're actually training your models on top of it. And what that means is it actually outperforms training on the raw data itself. So you can use, to get the same level of performance of training on the raw data, you can use 10 times fewer labels. And once you're in the region of 3 times fewer labels, you can actually outperform training on the raw data itself. And so you're not having to spend your precious labels, which are actually quite hard to get or sometimes even dangerous to get, in order to do that. The paper has about 6 different examples of where we've done this for different things, like canopy height. We've done it for crop detection, crop yield, all those kind of problems. So I do recommend having a look at the paper. Now, challenges. The hard part of this embeddings as data paradigm is actually making sure you have the embeddings. So this is our current progress. So where we have something in blue, that means that we have got the embedding there at 10-meter resolution for 2024. Where it's green, we've got the full 8 years. Each year of embeddings takes 20,000 GPU hours and 2 million CPU hours and requires 200 terabytes of online storage for that embedding. Because it turns out the world is surprisingly big at 10 meters. And so that's one of the biggest challenges we've got is actually doing this. And if you go to our GeoTessera repository, which I'll link in a second, you can actually see this updating over time as more embeddings are produced on the university's GPU clusters. Which brings us on to GeoTessera. So it's a Python library. We've got a camel version in the works, but it has a simple high-level API, and it lets you give it a bounding box and find embeddings within that bounding box. It downloads them, it caches them, and it also does the coordinate reference transforms, because it turns out actually uniquely identifying a point on Earth is very hard. And so there's multiple different ways you can do it, all of which have their own trade-offs, and you need to make sure that you transform between them, otherwise things go wrong. The library itself integrates with the existing ecosystem, so you can get NumPy arrays out, you can also get geotiffs out, and it supports lazy iteration of embeddings, so that you can do a computation over a very large area, but with only a small fixed memory overhead, which is actually, given the size of the embeddings, is actually really useful. So now I'm going to do a demo, and the demo we're going to do is, the hard part is going to actually be seeing the screen here. Okay, so this is some code. We're going to go through this code in a second, but what I need to do is find, oh, there we go. Oh, that's the way to do it. Right, I'm going to leave this code running. Oh no, I've run it. Right, so this is the UK. And what we've done, what we're going to do is, our problem is going to be, can we find solar farms? So here is some solar farms that we have labeled by hand, somewhere in the kind of west of the UK. And if we zoom in on these pink points, you can see that there's solar farms. And we've also picked a random sample of points that are not solar farms. And that's our training set. We then have a test set, which we spatially separated. Very important for geospatial tasks, because there's a lot of spatial autocorrelation. So we've created a separate test set. And then what we're going to do is we are going to step through this program. So what we do is we load up our bounding box. Bounding box is just the longitude and latitude that determines the area we want to do the computation on. We load our positive, negative for train and test. And then what we do, this is GeoTessera, GT. So we take our bounding box and you call fetch embeddings, and that gives you a generator which lets you iterate over the embeddings. We also need to know how many embeddings we have, just so we can give you a nice, pretty progress bar. And then what we do is we'll build up these matrices of embeddings. So for each of the labeled points where we have a longitude and latitude, we find the embedding at that point, and we build up these matrices, and we do it here. This is where we're actually iterating through the embeddings, and we're finding all the points. We're finding the nearest embedding for each of those. Then we can visualize those embeddings. So what I'm going to show you here. So how many people here are familiar with UMAP or TSNE? So these are algorithms for unsupervised dimensionality reduction. So we have 128 dimensions is the embedding. It's quite difficult to visualize 128 dimensions. So you want to reduce them down to 2 dimensions. So what we've done is we've reduced the embeddings down to 2 dimensions, and then we've colored them based on whether there's a solar farm or not, right? And you can see that those embeddings are incredibly rich, because actually they almost cluster immediately into 2 clusters that are totally separated. And on one side, you've got the solar farm, and the other side you haven't. So if we were to then run this code, what we would see is we ran it, and what we did is we've gone through and we've rerun it a number of times with different numbers of labels. So with just 2 labels, so just one positive and one negative, we already hit 88% accuracy on classifying these things. If you've got 10 labels, so 5 of each, you can already get up to 98%, and it just keeps on climbing from there. And this is with a very, very simple pixel-wise logistic regression classifier, right? So this is probably the simplest classifier you can imagine. It's a single linear layer, and we are training pixel-wise. So just there's no spatial information. If you were going to do this as a kind of production thing, you would almost certainly want to have some kind of convolutional neural network that takes into consideration some spatial information. So this is the output, and we'll zoom in here. So this is the test set. So it's not been seen in training, and you can see that these black areas here are the ones that the models end up. So white is no solar farm, black is solar farm. And you can see that even an incredibly simple linear model put on top of those embeddings is able to, sorry, it's a bit laggy, is able to actually identify where there is a solar farm. And so that's the quick demo. And we have less than a minute for questions.
Hello? It's working? Okay. Yeah, okay. So thanks. Very cool. I mean, I worked on this, so I also think it's cool. But I have a question. So this is basically compressing the information within the year of satellite imagery to a 128-dimension embedding. So that's very good for doing correlations and classifications like these. But if you think from the perspective of an ecologist, they want something like in DVI, they have theory for like why that correlates or is causal to something that they want to predict. How do we convince, or how do we make sure that this is something that people would actually want to use?
Well, we know it's something that people actually want to use because we've been doing workshops where we've taken ecologists who would otherwise not have done this because it would have taken years or longer of analysis of remote sensing data to do, and they've got results within kind of half an hour of labeling, thanks to actually to your system. So it's a bit of a plant question. In terms of interpretability, that's something where we have to borrow a lot of what's happening in the LLM space for interpretability. So we've got a project where we're then trying to do sparse encoders on top of this to look for features that we can then label and say these particular features indicate this property and that property. But from the embeddings themselves, they're just dense 128-dimensional representations. So they don't necessarily have anything interpretable about them until you do that work.
Right. One follow-up to that is about the economics of this. So it's obviously a very big challenge to get all the embeddings, and we do want to provide them so people could work on this without duplicating work of doing inference. But given that models are still evolving, and you would expect that there would be new models with better architecture, who would be paying for this? Like, we cannot reasonably regenerate everything across the world every time that there's a new model, right?
No, but in the grand scheme of things, while 20,000 hours is a lot of GPU time, it's actually relatively small compared with like how much GPU time you'd spend on, say, training even a small LLM, right? So for the productivity increase that we've seen from the users of this, even just this level is probably fine. Thank you.
Any other questions?
Well, Tim.
So this is identifying a fairly regular structure
Yeah.
in solar farms. Can you apply this to sort of find more organic sort of structures in the landscape?
Yes. So the thing to point out here, this is pixel-wise, so it's looking at every single 10-meter pixel, right? So it's not even considering that, oh, I've got this pixel that's likely to be a solar thing, and actually it's in the middle of a playground, right? If you were to use, if you were to include the spatial structure, so with something like a convolutional neural network, you can identify those kinds of structures. And we've got work in that, and the paper actually has an example of one of those.